Okay, continuing on, ocean acidification. In addition to being a radiative forcing agent, CO2 also forces the ocean chemically. CO2 enters the ocean via air-sea gas exchange. Acid-base reactions between CO2 and seawater cause the concentration of protons, H plus is protons, which is basically a hydrogen ion, to increase, and that of CO3 minus 2, this is the carbonate ion, to decrease. This leads to a decrease in the saturation of seawater with respect to the mineral calcium carbonate. That is, calcium carbonate tends to dissolve once the acidified seawater crosses the boundary between oversaturation and undersaturation. This is what's called the calcite compensation depth, or CCD. Typically, below the calcite compensation depth, calcium carbonate can dissolve in solution. Above it, it precipitates out. Well, we're finding that the calcite compensation depth is getting shallower and shallower. It's shoaling. So in other words, more and more organisms are at risk of basically having their shells, their homes, dissolve out from under them. This threshold differs for the various forms of calcium carbonate. We have calcite, aragonite, high magnesium calcite, but I'm not going to get into the weeds on that one. But the main point here is many marine organisms have shells or skeletal structures made of these mineral formed calcium carbonate, particularly vulnerable to ocean acidification. And then they talk about pteropods, so on. The changes to the marine carbonate system that have occurred since the Industrial Revolution are already unprecedented within the last 65 million years. Ocean acidification conditions will continue for many centuries in the ocean interior after the reduction of carbon emissions to net zero. And they give a few other specifics, but that's the main point here, is that acidification is going to harm marine organisms. Cumulative effects of warming, oxygen loss, pH decline, increasing acidity, may impact synergistically marine biota and may, in some cases, lead to ecosystem regime shifts. What they're talking about here is these different factors here, the warming, the oxygen decline, the pH decline, the increasing CO2, right? They do not necessarily act on their own, but that they can work with the warming, with the oxygen loss, to even further exacerbate whatever the ramifications are. It's almost like when they work synergistically together, it's even a further cumulative affecting or forcing. Marine regime shifts are often caused by multiple factors, either climate-induced changes or other confounding factors such as overfishing, high human-made nutrient input from land invasive species. Extreme ocean weather events, marine heat waves, high acidity, low saturation state events can have severe consequences for marine biodiversity. And when you take this all cumulatively, it can lead to a big problem. Besides the sea surface, where warming and acidification are strongest, also the intermediate waters, especially for the eastern tropical Pacific oxygen minimum zone, and deep water domains, such as the deep North Atlantic Ocean, are changing. This is of importance to deep sea ecosystems that are adapted to stable conditions, and we're making those conditions unstable. Even small changes can have disproportionate impacts. So here, this figure here, candidates for high probability, high impact marine tipping elements that concern warming, deoxygenation, ocean acidification, as well as their impacts. And then they say the areas in the map are approximate. So let's take a look at the figure here. So we'll start here in this red dashing here, Arctic sea ice reduction. Okay, And that's, of course, all up in here in the Arctic Ocean. That should not be a surprise. But associated with that is the thawing of the marine permafrost, which I discussed in my sea ice video, as well as polar acidification as well. Okay. We know about terrestrial permafrost thaw. I've now established with you that the marine permafrost is also thawing due to the heat content of the water moving into the Arctic Ocean. Okay, so we'll start now over here, and I guess you call that pink. Coastal acidification and deoxygenation. So that, as you can see right here off the eastern seaboard, Gulf of Mexico coast and Pacific coast, and then the Mediterranean, all up in Scandinavia, right? Some spots along the African coast, and then the east coast of the Asian continent. We're seeing coastal acidification, deoxygenation. Open ocean deoxygenation, that's the gray region. That's the Eastern Pacific that we just discussed. And then we see some of that off the coast, west coast of Africa. Okay. The yellow is warm water coral reef degradation, primarily affecting, Indonesia regime, and of course the Great Barrier Reef of Australia. Large-scale ocean circulation changes. All right, here's the North Atlantic, right? We know this is where the deep water formation begins. This is being affected. This is slowing down. We're not getting the conveyor belt. We're not getting the sequestration of CO2 and heat, as well as oxygen, to the lower depths that the ecosystems at depth need that oxygen. And removal of CO2 and heat from the surface to depth is a help in mitigating warming effect. Well, the oceans are stratifying. The thermal hailing currents are slowing. That sequestration is not going to be as great, and it probably is on its way to stopping. That is going to have profound changes for the upper ocean, stratifying them, affecting the productivity, and then not to mention what it does, in the atmosphere and globally as well. So this is huge here. So now you're going to say, what's being affected here? Off the coast of Antarctica, you have the Antarctic bottom water that comes off. This is very, very dense water, and it literally just dives to the bottom. It typically flows northward, and we talk about the North Atlantic deep water. The North Atlantic deep water actually flows over the Antarctic bottom water. So this Antarctic bottom water is the most dense water, oceanic water. It actually goes underneath the traditionally historical North Atlantic deep water. So that's a major issue there. Then the blue areas refer to changes in what's happening with El Nino and monsoon alterations. I prefer to refer this as the ENSO cycles. So the concerns are that we may be tipping the Eastern Pacific into a permanent El Nino state. That's basically what they're saying. And of course, the light blue is the global ocean, open ocean warming and marine heat waves, open ocean acidification, and not surprisingly, that's pretty much the rest of the oceans, pretty much all of the oceans. So they're basically identifying what's taking place and giving you a general idea of what areas are seeing the greatest impacts. So this kind of maps it out for you. Okay. And then they talk about, the candidates. It said, I will leave the URL in the comments section. You can read through the specific. But, in this paragraph here, they're talking about what I just discussed with you in looking at that figure. And we have differing time scales for the ocean. The upper ocean, the several few hundred meters, mixes on a time scale of decades, while the deep ocean water masses are renewed from the surface on a much longer time scale, 100 years to thousands of years. The deep ocean can be altered by climate change irreversibly for thousands of years, with the extent of the alteration dependent on the total change in climate forcing over time. Okay. A lot of what goes on here, of course, you have the Photic Zone, a couple, upper 100 or so meters. It could be, several hundred meters. That's typically the Photic Zone. And that can, have some effects on the scales of decades. The ocean is the major heat and net carbon uptake reservoir, referred to as a sink. Without ocean uptake, this is an important sentence. Okay, let me highlight that. Without ocean uptake, atmospheric warming would already be much higher. As I discussed in the ocean heat content video, 93% of greenhouse gas emissions since 1971 have been absorbed by the ocean. The remaining 7% has been in the atmosphere. That 7% has done all that we've already seen and we've already measured, observed. That 7% has caused all the melting of the ice sheet, has caused the warming of basically 1.5 degrees C, has caused the terrestrial permafrost to be thawing, as well as now the marine permafrost. That 7% has done all that. If the oceans hadn't absorbed as much as they have absorbed, the 93%, the changes would be even more pronounced and I would argue, catastrophic. Present-day anomalies relative to the pre-industrial of heat and anthropogenic carbon, hence pH, are initially largest at the ocean surface, where you're going to get the mixing. Then physical processes move it around, horizontally, vertically, what have you. Through mixing and ocean currents, the anomalies for heat and carbon are transported away from the surface and to deeper layers, from intermediate water layers down to deep and bottom waters. The amelioration of climate change is paid for by consequent changes in seawater properties and the resulting adverse effects on marine ecosystem. Apart from the decrease in solubility of oxygen with temperature, changes in circulation alter both the supply of oxygen to the deep ocean and the consumption of oxygen due to organic matter degradation. The timescales of the global ocean circulation from the surface throughout the deep waters, that's figure 3, I'll get to that in a moment, have two consequences. The vertical mixing cannot prevent a strong accumulation of heat and carbon accompanied by pH reduction in the upper ocean above about 1,000 meters if the forcing for heat and carbon is faster than the mixing of upper ocean and deep ocean. Okay? Let's think about that. The vertical mixing cannot prevent a strong accumulation of heat and carbon in the upper ocean, the upper 1,000 meters or so, if the forcing for heat and carbon is faster than the mixing. In other words, the input is faster than the sequestration can take place. That's basically what they're saying there. So in other words, overwhelming the system, they can't keep up. 2, deep mixing, mainly at high latitude convective sites, transports parts of the surface anomalies to greater depth, where long-lasting departures from natural values gradually build up over volume of the ocean water. Strong hysteresis behavior with the delayed recovery of environmental variables such as temperature or O2 is even projected under strong hypothetical carbon dioxide removal from the atmosphere. So if there's going to be any mixing, it's going to pretty much take place at high latitudes. And even that's being affected. So let's take a look at figure 3 here. Time scale of the large-scale ocean mixing and circulation. Okay, time scale of ocean mixing circulation. Okay, so here we have the sinking. 0 years, that's taking place now. Got a little bit of sinking off Labrador, right, off that way. Blue and purple are the colder waters, the red are the warmer waters, and they tend to be surface waters. Now, Wally Broker showed that if you were to follow, in general, if you were to follow a parcel of water as it traveled through the conveyor belt, it takes about 540 years to circulate around. General. Okay, depending on which pathway, because it does bifurcate and split into these different flows. So depending on which one the parcel of water finds itself on, it could take a little longer. And it obviously makes sense that you can go into the Northern Pacific, it can take 1,300 years. But now think about it. If it takes that long to mix the deep waters, that means the effects, the changes that are happening, is going to take that much longer to, say, recover. Now, this 500-year, could be traveling down to the South Atlantic. This sinking here, this is referring to the deep water coming off the continent of Antarctica, very cold water, right? And that moves northward. Not indicated here, but it does. And then we have over here about, in this region here, is the Antarctic Diversion Zone, right? Because you follow this here, we have the sinking, it comes up right here. See how this bifurcates this way and this way? This is the Antarctic Diversion Zone. This is where we have the upwelling, bringing all the nutrients that basically fuels the ecosystem of the southern oceans. And this part of this can become entrained in the Antarctic circumpolar current. Part of it can be entrained in other currents. Some will split, move into the Pacific Ocean. Some split goes into the Indian Ocean. So you can see all the different possible pathways this water can move as it sinks and flows. And then, of course, this is the return into the Gulf of Mexico region. This is basically a Gulf Stream into the Jinsea. So you got an idea of some of the length of time for these movements to take place. Again, surface currents are going to be warmer. They're going to be highlighted in a warmer color. And if you look at it, you can see how this goes over this. So yeah, it's a shallower current. That's a deeper current. Here's the return flow. So you can have one branch that splits off, goes into the ocean, and then returns immediately, or it splits off and continues on into the Pacific Ocean. So there you have it. So that's showing the time scales for mixing and circulation. So what do they say here? For mitigation climate change, the timescale aspects are important for greenhouse gas emission reduction. The more the release of CO2 and other forcing agents to the atmosphere slows, the more efficiently excess heat, excess carbon can be transported into the deep sea, right? That's basically what, statement one here, that says that if the input is much higher, it can't keep up, you can't do the sequestration. If you mitigate the input of CO2 and other forcing agents, then you can increase the mitigation, you can increase the sequestration rates. The smaller the buildup of heat and carbon anomalies at the sea surface acting to prevent critical tipping points in the surface of the upper ocean. So in other words, if you can pull carbon off the surface, it helps the surface deal with it. The smaller the total amount of emitted CO2 becomes, the smaller the accumulation of heat and carbon in the deep sea will be, the smaller the risk for high magnitude irreversible change. Now they talk about mitigation pathways to avoid ocean tipping points. The adverse impacts of human-induced climate change on the ocean can still be minimized. Earth system targets like global warming, ocean acidification levels, corresponding emission reduction age targets need to be ID'd, agreed on, implemented, verified. And then they highlight 6 areas, research topics, where Earth system scientists are contributing to the development and implementation of mitigation actions. 1, identifying the hotspots of high probability, high impact tipping points in the ocean, understanding their dynamics. Scientists are employing Earth observation and a hierarchy of models, from high-resolution regional models to global models of the ocean Earth system, to determine the areas where the most severe hazards have occurred in the past, decades to millions of years. where they're currently occurring and may occur in the future. And they discuss how they, determine, the probabilities and so forth. And they talk about, the type of data required, preferably as current as possible. Another goal would be to identify important forecast failures and why they failed. And then the Copernicus EU, basically Copernicus, that's a satellite system that can collect data continuously. And by the way, I should make a point that the U.S. is losing a number of satellites that they can access to collect data. The Europeans are taking the lead on this, as are also Asian scientists. The U.S. is falling behind. I have to bluntly state that. Assessing ecological tipping points caused by changes in physical, biogeochemical, ocean variables. So then they describe what they want to look at and what what they plan to do as far as understanding these processes. Identifying multiple mitigation targets to avoid ocean tipping point and to remain in safe operating space. Main environmental metrics employed to date in relation to climate change mitigation are atmospheric CO2 concentrations, global mean surface temperature. The simplicity of such metrics has contributed to the basis for the Paris Agreement, which had, was lacking in teeth, let's just say. However, in order to avoid critical tipping points, more refined emission mitigation limits need to be developed and applied. And we know that ain't happening. And then they cite the Arctic Monitoring Assessment Program on, Arctic climate impact assessment, snow, water, ice, permafrost assessments, highlight the importance of the Arctic region. Yeah, things are crazily going on in the Arctic. Assessing different greenhouse gas emission scenarios, the extent, the timing to meet the mitigation targets. Well, we know that the governments have been a whopping failure on that, with some minor things being done here and there. For example, in Germany, there's a move to put solar panels on all the houses. Okay, fine. But you got to keep one thing in mind. To build the technology is often greenhouse gas intensive. In other words, to get the materials to make, say, the solar panels uses a lot of greenhouse gases. You're burning a lot of fossil fuels. And you're doing environmental degradation because you got to go mine the raw materials. So I said it before, getting to net zero, while a laudable goal, is really probably not practical and not really likely to happen. Want to evaluate CO2 removal, solar radiation management, ocean mitigation options. Obviously, you want to reduce greenhouse gas emissions. And there's a whole bunch of methods and technologies being used to try and, aim to deliberately alter the climate system. Translation, geoengineering. Most of you know, I think geoengineering schemes are not practical. They certainly do not give you the desired results, and often there are unforeseen complications not considered, and that can basically bite you in the ass. Like, CO2, let's remove that from the atmosphere, ocean, and store it. Okay, I just did a recent short video saying how these schemes are really kind of silly. Then communicating to the stakeholders. Well, okay. I think those of us who have a stake in it would include humanity. So if they want to talk about, the science being more proactive with the public in communicating their findings and their recommendations, I'm all in favor of that. That's for sure. And scientists also talk about uncertainty. That's, nothing's 100%. You want to identify the uncertainty. You also want to identify the likely probabilities. You also want to say what the causes of the uncertainty are and how they can be addressed. And they highlight 4 promising options in Earth systems management. Okay, so let's go through this. Greenhouse gas emission reductions need to be realized. Okay? The highest priority for ocean damage limitation is the immediate drastic reduction of greenhouse gas emissions, especially CO2, since they drive ocean acidification as well as global warming and, as a consequence, deoxygenation. The smaller the excess carbon heat uptake will be, the smaller the long-lasting changes. Okay. A sound global resource management needs to be implemented. To achieve emission reductions, human societies need to tackle the transformation to decarbonized energy production, sustainable use of land and ocean, including food production, climate-friendly urban, as well as regional planning. Confounding ecosystem stresses such as overfishing, contamination with plastics, organic pollutants, as well as other hazardous substances, eutrophication, need to be addressed in parallel to reducing CO2. Okay, well, I'm going to go through here, and then I'm going to have some comments to make. And then that will be the end of it, because then we have all these references down below. Number 3, implementation and mitigation measures needs to be enabled through adequate governance structures and seamless interagency action. Mitigation measures must build on adequate implementation mechanisms, agencies ranging from intergovernmental organizations to societal sector ministries and local authorities and networks need to work hand in hand with clear responsibilities and obligations. This is a lot of hand waving, in my opinion. Sorry, it just is. We need to do this and do that, and nothing ever happens. And once again, scientists make recommendations. It's the politicians that need to implement the policy recommendations. Transformations need to be carried out increasingly fast. The support for significant societal transformation to avoid triggering harmful Earth system tipping point is progressing. For example, the EU has the goal to become carbon neutral by the year 2050. Might be too bloody late by then. Climate change in the ocean is manifesting itself clearly now. The cross-chapter assessment of potentially abrupt and irreversible phenomena related to the ocean and the cryosphere, published by the IPCC in a special report on the ocean and cryosphere in a changing climate, lists ocean deoxygenation, ocean acidification as irreversible for centuries to millennia at death. Abrupt physical ocean changes due to marine heat waves are expected with very high likelihood and high confidence concerning negative impacts on ecosystems. So what they're basically saying with high likelihood, high confidence is mean that the probability of these things happening is high. That's basically what that's saying. The physical, chemical, biological ocean systems are on the verge of tipping into another state, and many oceanic regions integrated over the world ocean. This adds up to a global issue of concern. Okay, now I want to address these 4 points here. Talking about CO2 emissions. And they talked about that this was what? An IPCC report. What's something we didn't see in this whole thing? Yeah, they talked about the permafrost, the marine permafrost. They did not mention methane. And all this warming has created a positive feedback loop of methane releases. Now, methane is a more powerful greenhouse gas. It traps more heat. Granted, it doesn't persist as long, but guess what? It oxidizes into CO2. So its effects will still be ongoing. Once again, the IPCC neglects methane. Once again. Now, they talk about here overfishing. Yes, overfishing is causing severe problems. I've talked with you guys about plastics before, and we know about the pollutants. I mentioned eutrophication earlier. What's something they're not talking about here? Why is there overfishing? There's overfishing because of overpopulation. There are simply too many people on the planet. You cannot have exponential population growth on a system with finite resources. More and more people are going to require more and more energy. We're going to require more and more food. We're going to require more and more space to live. And not to mention grow food. Not to mention, okay, and I know this is related to the ocean, so they're not going to talk about terrestrial stuff. But don't forget, crop yields are declining and the nutritional values are declining. We've already seen the heat waves and the fires and so on. Look what just happened, 100 degrees, 106 degrees in Seattle, Portland. Good God, that's unheard of. 119, 125 degrees ground temperature in Siberia. And of course, we have the 200 plus zettajoule of ocean heat energy. 68% of that in the upper 500 meters. Okay, so this is all. Kudos to the authors for pulling this literature review together and bringing in all the findings from all these papers. Kudos to them for that, but I just don't see these mitigation taking place. I just don't see it. And when you look at a lot of the positive feedback loops that have already been set forth in action, I find it difficult. I find it difficult to reverse this. And just the thermal inertia alone will make reversing this difficult. So they are correct that some of these changes are going to be on the scale of centuries to millennia. They're correct on that. Reversing this, I've got a bridge to sell you if you believe that. Something I wanted to, I wanted just to share this with you because, they're identifying some of what's going on in the ocean. They're pulling together a shitload of research papers. So, this, by leaving you the URL link, you can, if you wish to, click on any of these papers referenced and read up on them for yourself. You can, if you're doing that. So now, as a final thing here, I want to show you this graphic from our good friend Zach Labe. Arctic sea ice is thinning, and these are sea ice thickness meters in June. So you go from 0, which means open water, to 5 meters thick. This is in June. Okay, so it's basically the springtime. Oceanic winter, the height of oceanic winter is in March. The height of oceanic summer is in September. So this is about halfway. This is basically, oceanic springtime, if you will. So he does this by decades: 1980 and 89, 90 and 99, 00 to 09, 10 to 19. And we see, this is when it's the thickest. So here's where we have like the 5 meter thick ice. This is the oldest sea ice here. Okay. A little bit of change in 90 to 99. Then we start seeing more change. We're starting losing, it's starting to shift this way. You notice, if you look here, the areas of white is declining. But now look at here. First of all, notice the open water by the Mackenzie River Delta. Notice the Chukchi Sea. Right? Here's the Chukchi Sea over here. Look at it here now. And this is thin ice. This is like maybe a meter thick. Okay? Chukchi Sea. This is where I did a lot of my research here, right in this area, folks. Chukchi over into the Beaufort sometimes. I couldn't go over to the East Siberian or Laptev Sea because, he needed certain documentation. That's Russian territory and so on. But yeah, we could work in the Chukchi over into the Beaufort. But you see how we have ice here? That's open water. There's open water. Open water. Look at that. More open water. And of course the Barents, because you have the North Atlantic water bringing in that heat there, it keeps that, pretty much ice-free, but it's becoming Atlantified. So this is something else this report failed to include. I mean, other than this little graphic. Where is that figure? Yeah, where they talk, oh yeah, here's the sea ice changing up there. But they didn't address it. I felt they should have needed to address that more so in the body of the text. So, there are tipping points that are in danger of being crossed in the oceans. Most people think of tipping points as we get to a certain temperature increase in the atmosphere. Well, the tipping points in the ocean that could lead to hypoxic zones, maybe dead zone, that could lead to, for example, a permanent El Nino condition and no more La Nina of the ENSO cycle, or that we're seeing the acidification issues where the CCD is getting shallower and shallower. That's going to kill organisms because they can't make their tests, their shell. We're seeing the acidification of the corals, right? We're losing deep water formation, which is ventilation, which allows for vertical mixing. That's going to affect the ecosystems at depth. Right? We're seeing all these things, and we're in danger of tipping into a new situation, a new type of system. That's kind of the point of why I wanted to do this video for you. So I've said it before, when you figure what all that's happening in the oceans, the heat, the acidification, the loss of oxygen, the stratification, the thermal haline flow slowing, overfishing, plus the productivity is decreasing, which means the number of phytoplanktons are decreasing, which means the atmospheric oxygen levels are decreasing. The situation is dire, and I'm going to be blunt. They can talk about the ocean tipping points here, and all these tipping points are telling us one thing: the oceans are dying. They are dying, and the tipping point is going to push them into the ocean's death knell. I'm being blunt here, but that's what's happening. So I thank you for your time. Hello folks, this is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.